Okay, let's dive into something pretty amazing. How we as humans learn to see something that's totally invisible. We are surrounded by forces we can't see, hear, or feel, and yet we figured out how to measure them. Let's get into how that's even possible.
I mean, that's the fundamental challenge here, right? Radiation is a basic part of our universe. It's everywhere. But our own senses give us zero clues that it's there. So how on earth did scientists even begin to crack this problem?
Well, here's the secret. The key isn't to see the radiation itself. It's to see the trail of evidence it leaves behind. So, in this explainer, we're going to uncover how scientists basically built a brand new sense, one that can perceive this invisible world just by tracking the tiny footprints radiation leaves when it moves through matter.
So, what exactly is this footprint? What are we actually looking for? Well, it all boils down to one single crucial interaction that pretty much every radiation detector is designed to spot, and it's called ionization.
And this is where it gets really clever. What you're seeing here is the universal clue that almost all detectors are hunting for. As a particle of radiation zips through a material, it bumps into atoms and boom, knocks an electron loose. This creates a tiny electrical imbalance, what's called an ion pair. And that little spark, that is the footprint we can actually measure.
And this is how we actually put a number on that effect. It's not enough to just see the footprints. We want to know how many there are. The absorbed dose, measured in a unit called grays, tells us exactly how much energy was left behind in the material. Think of it as measuring the density of those ionization footprints. It gives us a real, solid value to describe something we can't see.
Okay, so now that we know what we're looking for, let's tackle the very first, most basic question you'd ask. Is there any radiation here at all? It all starts with just counting those footprints, one by one.
This slide does a great job of showing the difference between two classic detectors. On the left, you've got a proportional counter. It's kind of subtle. The size of the electrical pulse it makes gives you a clue about the radiation's energy. But then, on the right, you have the famous Geiger counter. It's totally different. Any little bit of radiation triggers this huge all-or-nothing avalanche of charge. It's not subtle at all. It's just a simple, loud alarm.
And this quote just nails it. It perfectly captures the whole idea of the Geiger-Müller tube, the thing that makes that iconic clicking sound. It really is the smoke alarm of radiation detection. It screams when there's radiation, and it tells you that something is there, but it has no idea what kind of radiation it is.
But, just knowing radiation is there often isn't enough. For most real science, we need to answer a much deeper question. What kind of radiation are we looking at? And this is where a much more sophisticated technique called spectroscopy comes into play.
So to identify the radiation, we need a detector that's less like a smoke alarm and way more like a piano tuner, something that can precisely identify the exact note or the energy of each particle it sees. We need a linear response, which is just a fancy way of saying that the size of the signal it puts out is directly tied to the energy of the radiation that came in.
This is where these amazing materials called scintillators come in. They literally flash with light when they get hit by radiation. And these properties here are what make them so useful. You need something that's really good at turning radiation energy into light. It needs to be clear so that light can actually get out, and it's got to be fast so you can count a lot of events without them blurring together.
And here's the crucial point. By measuring the brightness of every single one of those little flashes, we can build an energy spectrum. Now, when a particle dumps all of its energy inside the detector, it creates this beautiful spike called a photopeak. The position of that peak on the energy graph is like a unique fingerprint. It tells us exactly what radioactive source we're looking at. No guesswork.
But of course, nothing's perfect. There are always trade-offs. This table compares two common types of high-res detectors. Scintillators on the left, they're super practical. They work at room temperature, they give you good results. But then you have semiconductor detectors, like germanium, on the right. Their energy resolution is just breathtakingly better. They can tell the difference between energies that are incredibly close together. The catch? You often have to cool them with liquid nitrogen to get them to work. It's a classic engineering choice, right? Performance versus practicality.
Yeah, making a perfect measurement would be nice, but it's never that simple, is it? In the real world, you have to deal with the messy business of trying to separate the true signal from all the other junk, all the background noise.
So, the first big challenge is something called dead time. For a tiny, tiny fraction of a second after a detector sees a particle, the whole system is busy processing that signal. And during that little moment, it's completely blind. It can't see any new radiation that might be coming in.
And you can probably guess why this is such a huge deal. If you don't mathematically correct for all those little blind spots, your measurements can be wildly wrong, especially in high radiation fields. You end up seriously underestimating how much radiation is actually there just because your detector was busy and missed some of the events.
The other major headache is just background radiation. You can stick your detector inside a giant lead shield, but it's still going to get hit by stray radiation from the universe. This chart shows that a big chunk of it comes from cosmic rays from space. But here's the ironic part. The biggest source is often tiny bits of natural radioactivity in the very lead shielding you're using to block everything out. You just can't win.
So let's just pull back for a second and look at the big picture here. This whole journey, from just simple counting to incredibly high-resolution spectroscopy, it's fundamentally changed our world by giving us this powerful new sense.
I mean, the ability to actually see and measure radiation has had this profound impact everywhere, from keeping people safe in nuclear power plants to analyzing ancient artifacts, all the way to powering life-saving medical tools like CT scanners. This technology is a silent but absolutely essential part of our modern world.
At the end of the day, the story of radiation detection is just this incredible testament to human ingenuity. It's about our unstoppable drive to build tools that expand our very perception of reality. And it really makes you wonder, doesn't it? What other invisible forces are out there shaping our world right now? And what new senses will we have to invent to finally see them?